Terraforming. The word itself evokes visions of epic transformation, of barren red deserts blooming into blue-green worlds fit for life. From early science fiction to the cutting edge of planetary science, the concept has captured humanity's imagination for generations. But beyond the dazzling images, what does terraforming actually require? What would it mean to turn Mars, a cold, airless wasteland, into a world that could support life as we know it? To truly understand the challenge, we must first define our terms, outline the requirements, and confront the staggering scale of planetary engineering. At its core, terraforming is more than building shelters or domes. It's the deliberate, sustained modification of a planet's environment to make it habitable by Earth life. This means changing the planet's temperature, thickening and reshaping its atmosphere, providing accessible water, and altering the surface conditions until they reach the delicate balance required for complex ecosystems. Imagine the difference. Colonization is surviving in spite of the planet, clinging to life inside fragile bubbles. Terraforming is transforming the planet itself, creating an environment where humans and Earth life could walk, breathe, and thrive under an open sky. To visualize the difference, picture the early images of Mars, dusty, windswept, with a thin, toxic atmosphere. Now picture those science fiction dreams, forests and rivers, clouds drifting in a blue sky, perhaps even animals grazing under the Martian sun. The gulf between these realities is vast, and the path from one to the other is riddled with scientific, ethical, and logistical hurdles. To create an Earth-like environment, Mars would need a breathable atmosphere, one with about 21% oxygen and 78% nitrogen, similar to what we have on Earth. It would need a surface pressure high enough to keep liquid water from boiling away, ideally above 0.6 atmospheres, far above the less than 1% of Earth's atmospheric pressure that Mars currently has. The surface temperature would need to be moderated, fluctuating between 0 and 40 degrees Celsius, rather than the current average of -60. The planet would need protection from ultraviolet radiation and cosmic rays, which today bombard the Martian surface unimpeded thanks to the absence of a global magnetic field. And, perhaps most crucially, Mars would need accessible liquid water, oceans, lakes, or rivers, to provide the foundation for life as we know it. This is a system of systems, a tapestry of interlocking changes, each dependent on the others. Terraforming is not a single action or invention, but a grand experiment in planetary engineering, one that unfolds over decades, centuries, or even millennia. Progress is slow, measured in increments, and failure can mean the difference between a new world and a lifeless desert. But even if the odds are long and the challenge is immense, the question remains. If we could transform an entire planet, if we could secure a second home for humanity, a backup for Earth itself, shouldn't we try? The question invites us to explore not just the science, but the society and philosophy behind planetary transformation. What methods are possible, and what are their consequences? What are the timelines, the costs, the alternatives? And ultimately, could any of this happen in our lifetime? Let's explore the methods scientists have proposed to terraform Mars, each a blend of innovation, audacity, and daunting complexity. First, consider the Martian atmosphere. Today, Mars's atmosphere is a thin wisp, barely 1% as dense as Earth's, and composed almost entirely of carbon dioxide. To make Mars hospitable for life, this needs to change. One approach is to thicken the atmosphere by releasing the carbon dioxide currently locked away in the planet's polar ice caps and regolith, the soil and rocks just below the surface. By artificially heating these reservoirs, perhaps with gigantic mirrors or targeted nuclear detonations, we could trigger the release of CO2, creating a runaway greenhouse effect. More greenhouse gases trap more heat, which in turn releases even more CO2. A positive feedback loop that could, in theory, warm the planet and thicken its atmosphere. But Mars is poor in nitrogen, a key ingredient for a breathable atmosphere. Some scientists have proposed a more radical solution, redirecting ammonia-rich asteroids from the outer solar system to crash into Mars. These cosmic impacts would not only deliver nitrogen, but also water vapor, further thickening the atmosphere and kick-starting chemical cycles necessary for life. The challenges here are immense. Decades of careful engineering, the risk of catastrophic impacts, and the sheer energy required to move asteroids across millions of kilometers. Yet, in the grand scheme of terraforming, such interventions may be necessary. Even with a thicker atmosphere, however, Mars faces another existential threat: the solar wind. Unlike Earth, Mars lacks a global magnetic field to shield it from the constant stream of charged particles emitted by the Sun. Over billions of years, this has stripped away much of Mars's original atmosphere, and any new atmosphere we create would be similarly vulnerable. To address this, NASA and other agencies have proposed constructing a magnetic shield. Perhaps a powerful magnetic field generator stationed at Mars's L1 Lagrange point, a location where it could deflect solar wind and protect the planet's atmosphere. This would not terraform Mars directly, but it would be a critical safeguard, ensuring that the hard-won gains of atmospheric thickening are not simply eroded away by the elements. With atmospheric protection in place, the next challenge is heat. Mars, on average, is far colder than Earth, with surface temperatures rarely rising above freezing. To melt the polar ice caps, free liquid water, and create habitable conditions, the planet must be warmed. Several methods have been proposed, deploying vast arrays of orbital mirrors to focus sunlight onto the surface, constructing fusion reactors to generate heat in key regions, and, most controversially, detonating nuclear devices above the poles to jumpstart warming. Each approach carries risks and uncertainties, but all share a common goal: to shift Mars' climate from frozen wasteland to temperate cradle for life. Water is the next essential ingredient. While Mars is dry on the surface, it holds substantial reserves of water ice in its poles, permafrost, and perhaps underground aquifers. By warming the planet and releasing this water, we could create rivers, lakes, and even shallow seas. This would require massive infrastructure, drilling, heating, careful atmospheric planning, to ensure that water remains liquid and doesn't simply escape into space. But if successful, it would provide the foundation for future ecosystems. With the basics in place, the final phase of terraforming could begin. Introducing life. Hardy, genetically engineered microbes could be seeded to help enrich the soil, fix nitrogen, and begin the slow process of building an Earth-like biosphere. Over time, more complex organisms could follow: plants, insects, and eventually, animals. This stage would be fraught with challenges, unknown interactions, unanticipated consequences, the risk of failure at every step. But it represents the culmination of centuries of planning, a Mars transformed from barren rock to living world. Yet, as we contemplate these grand ambitions, we must also consider the ethical and environmental dilemmas they raise. What if life already exists on Mars? For decades, scientists have speculated that deep beneath the surface, in pockets of water or briny soil, microbial life could survive. If we terraform Mars, we risk destroying this native biology, overwriting an alien ecosystem before we ever truly understand it. Is it ethical to pursue our own survival at the expense of another world's natural history? Some advocate for a hands-off approach, a policy of planetary protection that preserves Mars as it is. Others argue that, if Martian life exists, it could be studied, protected, and perhaps even integrated into a new biosphere. The answer is far from simple, and may ultimately shape the future of planetary exploration. International treaties currently ban harmful contamination of other worlds, and the Outer Space Treaty of 1967 enshrines the principle of planetary protection. Terraforming, by its very nature, could violate these agreements, requiring new laws, new protocols, and unprecedented cooperation between nations and agencies. Even more fundamentally, we must ask, are we repeating our mistakes? If we have struggled to protect Earth, our only home, what gives us the right to reshape another planet? Terraforming is not just science. It is philosophy. It reflects our values, our limitations, and our aspirations. It is a mirror showing us what kind of species we have become and what kind we hope to be. Turning from the philosophical to the practical, what are the timelines for terraforming Mars? Could it truly happen in our lifetime? Let's break it down into phases. In the short term, the next 30 years, the focus will likely be on establishing a permanent Mars base. By the 2040s, we may see the first human outposts, greenhouse domes with experimental ecosystems, water extraction from ice, and small-scale atmospheric processors designed to test and refine our technologies. These early steps will be incremental, but critical, laying the groundwork for future expansion. In the midterm, 50 to 100 years, the goal would be to partially warm the surface, release CO2 from the regolith, deploy magnetic shielding infrastructure, and create self-sustaining Martian habitats. These milestones would represent a transition, from survival to transformation, from isolated colonies to a planet in flux. The long-term vision, stretching over 100 to 500 years, would see full atmospheric transformation, the stabilization of liquid water, and the gradual introduction of Earth life on a planetary scale. This is not a quick fix, but an intergenerational relay race, one that would demand the patience, determination, and creativity of countless generations. Which brings us to the question of cost. Terraforming Mars would be, by any measure, the most expensive project in human history. Conservative estimates run into the trillions of dollars, encompassing thousands of rocket launches, the construction of lunar and Martian industries, the development of fusion power, and the mobilization of global or multinational collaboration. The sheer scale of the undertaking is staggering, dwarfing even the greatest engineering feats of the past. Will terraforming be a public mission, a collective enterprise uniting nations and peoples, or will it become a private space race, driven by competition and profit? The answer will depend on our values, our institutions, and our willingness to see beyond short-term interests. But terraforming is not the only path to making Mars livable. There are alternative futures, each with its own advantages and challenges. One option is to rely on sealed environments, biodomes with regulated atmospheres, underground bases shielded from radiation, and small-scale ecosystems tailored to human needs. This approach would avoid the need for planetary-scale engineering, but at the cost of living in perpetual confinement, never truly free to breathe Mars air or walk its surface unprotected. Another possibility is to construct orbiting habitats, spinning space stations with artificial gravity, solar-powered farming rings, and complete independence from planetary conditions. These habitats could be located around Mars, Earth, or elsewhere in the solar system, offering flexibility, mobility, and resilience against planetary disasters. But they would also require massive investment, advanced technology, and new solutions to the challenges of long-term life in space. A third option is to consider terraforming other worlds entirely. The Moon, which is closer but even less hospitable than Mars. Venus, with its thick atmosphere and scorching temperatures. Or Titan, Saturn's largest moon, rich in resources but freezing cold. Each presents unique challenges, and for now, Mars remains the most accessible and promising candidate for terraforming. Which brings us back to the fundamental question: could we terraform Mars in our lifetime? Visionaries like Elon Musk believe that a self-sustaining city on Mars could be built by 2050. NASA is developing the technology now. Robotic explorers, advanced propulsion systems, synthetic biology, and artificial intelligence. These tools are changing the rules of what's possible, accelerating the timeline from the realm of science fiction into the domain of near-future engineering. In truth, the full terraforming of Mars, a breathable atmosphere, flowing water, thriving ecosystems, will almost certainly take centuries. It is unlikely to be completed within the lifetime of anyone alive today. But the first steps, the laying of infrastructure, the building of habitats, the seeding of microbial life, could begin within decades. The first humans to set foot on Martian soil may also be the ones who plant the seeds of its eventual rebirth. Terraforming Mars is, at its heart, a mission not just to change a planet, but to change ourselves. It is an expression of our deepest aspirations, to become a species that does not merely adapt to the universe, but shapes it. To survive not as fragile passengers, but as architects of our own destiny. The process will be fraught with challenges, setbacks, and difficult choices. We will be forced to confront not just the limits of our technology, but the limits of our wisdom and responsibility. We will have to invent new tools, new laws, and new forms of cooperation. We will need patience, humility, and unwavering commitment. But if we succeed, if we transform Mars from a lifeless desert into a world teeming with life, we will have achieved something unprecedented in the history of the cosmos. We will have become the first species to create a new Earth, to bring life to a barren world, and to ensure the survival of our civilization for millennia to come. The story of terraforming Mars is still being written. Each new discovery, each technological breakthrough brings us closer to the dream. Whether the process takes decades or centuries, whether it is begun by governments, corporations, or a new generation of explorers, it will require the courage to imagine, the discipline to plan, and the resolve to act. As you listen to these words, remember, we are living in the only time in history where this conversation is possible. We are no longer just imagining Mars. We are building the tools to go there, to stay, and perhaps to change the planet itself. Ask yourself, what kind of world do we want to build? What legacy do we want to leave for future generations? The answer may lie not just on the red sands of Mars, but in our willingness to dream, to strive, and to reach for the stars. Terraforming Mars is not just a scientific challenge. It is a test of our values, our vision, and our hope for the future. The journey may be long, the obstacles daunting, but the rewards, new worlds, new possibilities, and a renewed sense of purpose, are worth the effort. In the end, the question is not just whether we can terraform Mars, but whether we are ready to become a species that takes responsibility not only for our own planet, but for the wider universe. The future is ours to shape, one step, one generation, one world at a time. So when you look up at the night sky and see that tiny red dot glowing in the darkness, remember, it is not just a planet. It is a canvas for our greatest ambitions, a testament to our capacity for wonder, for discovery, and for transformation. Whether or not we live to see a green and blue Mars, the journey itself will define us, challenge us, and inspire us for generations to come.